Today we're going to talk about Lesson 23, Decimals. Mathematicians denote the separation point of the units digit and the tenths digit by writing a decimal point. So to the left side of the decimal point, you're going to see in our graphic on the next slide that we begin with the units digit. On the right side of the decimal point, we begin with the tenths digit. Decimal actually comes from the Latin prefix deci, which means 10. This makes sense since we use the base 10 number system. You may also see numbers written in the forms that we traditionally call decimals, called decimal fractions. Decimal fractions and decimals mean exactly the same thing. So don't be surprised if you hear the word decimal fractions. They simply mean decimals. Look at this graphic. You see that positions to the left of our decimal point represent place values that are in increasing powers of 10. We have ones, tens, hundred, thousands, 10,000s, 100,000s, and millions. We're getting larger by powers of 10 as we move to the left. On the right side, if we move to the right, you'll see that the positions to the right of the decimal point are actually decreasing powers of 10s. Also notice that we do not begin with the units digit on the right side of the decimal point, as we were just talking about. It's going to begin with the tenths digit. Notice the THS on the end of each of these. Tenths, hundreds, thousands, 10,000s, and etc. Let's talk about how we read and write decimals. Now, if our number is less than 1, we're going to skip these first two steps. So if there's no number in front of your decimal point, we will not need to do this. But if they are, you're going to read to the left part of the decimal. You read that whole number part as usual. When you get to the decimal point, you read that as and, or write it. And then you're going to read the number to the right just as if it were a whole number until you get to the last digit. Then you're going to say the place value of that last digit. Let's look at some examples. The first example is 8.8951. How would we read or write that? So we're going to look to the left and we're going to read that as a whole number. 8, the decimal point as the word and. So 8 and we're going to read to the right of the decimal place just like it was a whole number. 8,951, and then put your place value of that last digit, which is 10,000s. So that would be 8 and 8,951 10,000s. In example B, we're going to read to the left of the decimal point as if it were a whole number, 18. We read the decimal point as the word and. Read the numbers to the right of the decimal point as a whole number, 25, and then put its place value. That's tenths, hundreds. So we're going to end with hundreds. 18 and 25 hundredths. Now let's talk about expressing decimal fractions. Again, decimals. In example 2, we're asked to express the value of the underlined digit as a fraction whose denominator is a power of 10. So if we look at part A, we're going to look and see what place value we have. The 5 is underlined, so that's tenths, hundredths. So if I were to write that as a decimal fraction, that is 5 over 100 because it's in the hundredths place value. In part B, again, we're writing with denominators of power of 10. So that's tenths, hundredths, thousands. And since the 9 is underlined, that would be 9 over 1,000. And the last one, the 3 is underlined. It's in the tenths place. So we would write that as 3/10. Notice here we're just expressing the value of the underlined digit. So your denominators will be powers of 10, your numerators will be the number that's underlined. Like whole numbers we've previously expressed in expanded form, we can do the same thing with decimals. Example 3 says write the expanded form of the decimal to show powers of 10. So we're going to start with a 9. Okay, 9 times 10 to the first, that's 9 times 10, that's going to give us 90. Plus 8 times 10 to the 0. Remember that 10 to the 0 is the whole number 1, so 8 times 1 is 8, so that gives us our 98. And then we're going to look at our place value. So this is the place value of 1, this is the place value of 0, this is the place value of -1, -2, and etc. Remember that as I'm moving to the left of the decimal point, I'm increasing those place values. And when I'm moving to the right, they're getting smaller and smaller by powers of 10. So this we would have 3 times 10 to the -1 and 2 times 10 to the -2. And that would be that number written in expanded form. So think about our place value. Here's our decimal point. We're going to go 10 to the 0, 10 to the first, 10 to the second, 10 to the third. And to the right side of that decimal point, 3 times 10 to the -1, 2 times 10 to the -2, and we would keep going if we had other numbers, 10 to the -3, 10 to the -4, and etc. Let's talk about inequality and equality of decimals. When we compare decimals, we're going to start with the greatest place value, and we're going to determine which number is greatest. If those digits are the same, then we're going to compare the digits in the next place value to the right. And we're going to keep comparing digits with the same place value until we find digits that are different. So let's take a look at what we're talking about here. If I want to compare 0.47 and 6, I'm going to start with the first place value. Well, 6 is larger than 0.47 or 0.4. So since 6 is larger, that means that 0.47 is less than 0.6. If we take a look at problem B, when I compare 0.7 and 0.3, 0.7 is greater than 0.3, so I don't have to look at any other values. But when I look at C and I want to compare them right now, the 3's are the same, so I have to keep moving. I go to the 2's, they're the same, so I have to keep moving. I go to 4, and so we're going to move over here, which is a 0. And so since 4 is greater than 0, 0.324 is greater than 0.32. If we look at question D, 5 is the same, 4 is the same. So now we're going to compare 0 and 2. And since 0 is less than 2, then 5.4 is less than 5.427. And we'll do the same thing with part E. The 3's are the same, the 8's are the same. So we add a 0, and since 5 is greater than 0, 3.85 would be greater than 3.8. Let's look at a series of numbers and try to compare which is greater. We have 0.19, 0.036, 0.195, and 0.2. So we're going to start in the tenths place value since we do not have a whole number in front. We have a 1, a 0, and a 2. Well, 2 is bigger than all those other numbers. So the one that would be greatest out of those 4 numbers is 0.2. Let's define terminating and repeating decimals. A terminating decimal, of course, we know is a decimal that stops. But how can we look at a fraction to determine if they're a terminating decimal or a repeating decimal? A terminating decimal is a fraction that has a denominator of prime factors of only 2 and 5. So to determine if a number is going to repeat or terminate as a decimal, you look at the fraction and you look at the denominator and you look at the prime factors. If we have only 2 and 5s, then they're going to terminate. If you take a look at that denominator and they have prime factors other than 2 and 5, that tells you that that fraction is going to turn into a repeating decimal. So let's look at some examples. Does the fraction terminate or repeat? This is example 6. So I look at 5, 6, and I think about the factors of the denominator 6. Well, I have 2 and 3. Because I have a factor other than 2 and 5 in there, this tells me that this is going to be a decimal that repeats. And if you divide that out, you're going to see we get 0.83 repeating. In part B, 1 over 80, if you look at the prime factorization of 80, that's 2 to the 4th times 5. I only have factors of 2 and 5. Because of that, I know that 1 over 80 would convert to a decimal that terminates, and if you divide that out, you get 0.0125. Put in your calculator and try it. 9 over 15, if we look at our denominator, what I did first of all, though, is I went ahead and reduced that. I noticed that I could divide both the numerator and denominator by 3, so I got 3/5. And then I have a factor of only 2 or a 5. Matter of fact, I only have a 5. So this tells me that 3/5 will terminate. And if you divide it out, it actually does. And it turns into the decimal 0.6. A couple more examples. Does the fraction terminate or repeat? So if we look at 7 over 15, take a look at your denominator. Again, it has factors in our prime factorization of that denominator of 3 and 5. So since it has factors other than 2 and 5, because it has that 3, it's going to repeat. And 3 over 14, we have factors of 2 and 7. And you're going to see here that the 1, 4, 2, 8, 5, and 7 do repeat. And again, it's going to be a repeating decimal because I have a factor of 7. I have a factor other than 2 and 5. So really easy to look at the denominator of a fraction and determine if that's going to turn into a decimal that terminates or repeats. So let's make a definition here. Let's talk about a repetin. A repetin is the repeating digits of a repeating decimal. So in example 7, we're going to write the decimal for each rational number, for each fraction, and we're just going to use a bar to show the repetin. What are the repeating digits of that repeating decimal? So if you take and you divide 3/11ths, you're going to see that I get 2/7, 0.27, and that 2 and 7 repeat. So the repetin will be 27. 1/3, this is a very common repeating decimal. If you take 1 and divide it by 3, you get 0.3, where the 3 is the repetin, or the repeating digit. 5 divided by 12, you see I get 0.416, but the only repetin that I have there is the 6. The only number that repeats is 6. Let's talk about rounding decimals. This is something that you really need to make sure you know how to do. This seems to be a weakness for a lot of college students. They cannot round correctly to a particular place value. So to round, you locate the place value to which the number is to be rounded. And so we can sometimes put an arrow or a check there. And we're going to look to the immediate right of that marked digit. If that digit is 4 or less, drop all the digits to the right and the number stays the same. If that number to the right is 5 or greater, then we're going to increase that number by 1, but again, all the digits to the right are dropped. Let's practice a few of these. I have an example 9, the decimal 633, 633, and 14216, 14,216 hundred thousandths. They ask us to round to the nearest hundred, okay? So we're going to look at the hundreds position. Notice there's no THS on that. They're asking us to round to the nearest hundred. So if we look at our hundreds place, I have a 6. So you look to the immediate right and check that number out. If that number is 4 or less, then that number 6 stays the same. All other digits become zeros. So that 6 is going to stay the same, and all these become zeros. We don't need to write 600.00. So if I rounded that to the nearest 100, my answer would be 600. Let's do a few more to practice. We're going to round each decimal, first of all, to the nearest tenth, and then we're going to go back and round it to the nearest hundredth. So if I look at my first example, 0.3, I look to the right, and because that 4 is 4 or less, that 3 stays the same, and then all these become zeros. So you can see that that rounded to the tenth would be 0.3. If I look at part B, the tenths place, then I look at the 8. That's my hundredths place. Since that is 5 or larger, I'm going to round that 0 up to a 1. And remember, all the digits below that or after that are 0, and we don't have to write that. So 0.1. 15.721, if I round to the tenths place, I look at the 7. When I take a look at the number to the right, that's a 2. So my 7 is going to stay the same. So that rounded to the tenths place would be 15 and 7/10. If we go back and we round to the hundredths place, 0.34, so I look at the hundredths place, that is the 4. This time I have a 7. So that 7 is going to cause the 4 to be rounded to a 5, and everything to the right is going to be zeros. If I round B to the hundredth, the number to the right of the hundredth is a 2, so the 8 stays the same. My answer is 0.08. And the last one, part C, the 2 is in the hundredths place. I look to the right, that's a 1, so my 2 is going to stay the same. I get 15.72. I can't emphasize how important it is to be able to round decimals correctly. Let's look at another example. In example 11, we're going to round 2.3528. I'm saying that the lazy way, but you should be able to write that out. 2 and 3,528 10,000ths to the given number of decimal place. So we're going to round it to the hundredths. So if I look in my hundredths place, that is a 5. I look to the right, that is a 2, so that means that that's 4 or less, so it stays a 5, and I get 2.35. If I round to the tenths place, my tenths place is a 3. When I look to the right of that 3, it's a 5. That means I'm going to take that 3 and move it up, so that becomes 2.4. Again, remember, once you round up, or once you stay the same, all the digits to the right become 0. And the last one is the thousandths. So in my thousandths place, I have a 2. So when I look to the right, it's an 8. That's going to make me move that 2 up to a 3. So 2.353.